Hey, Harsha.
Hello.
Hey. Yeah, I was thinking there will be no one. Glad to see you.
Oh, okay.
I mean, you guys are only two of you guys, so it's
I
understandable.
actually forgot about Tuesday's class again.
Yeah, that's okay. Yeah. I think as of now, I have not yet taught an empty classroom. I think never in my life, I guess. So I was thinking this might be the first day I will be doing it. I think in this class, this might happen. I have the suspicion that this might happen. Well, we'll see how it goes. I mean, it's pretty much like these days conferences. You record your talk and then it is played.
Available
It's
online.
sort of that takes away the.
Yeah, even teaching online sounds very bad. I mean, you can't.
Yeah,
The students are not there in the class.
yeah. Well, okay, we'll give it a few more minutes. I think I expect maybe Ken might be there. I mean, he's not missed a class yet. But, yeah. How are things going with you?
They're okay.
Yeah.
Everything's fine. Yeah.
You're supposed to take the other exams also. I
I
didn't.
was gonna send you an email, but yeah. The Are you taking the electromagnetism 2 as well this time?
Yes. So I think look back in your in your. I think there was this
Two
so-called
semesters
contract.
ago.
There was a contract signed, right?
Yeah.
So yeah, feel free to talk if you want to in my office hours or something. I mean, this is getting recorded just for your information, so it's up to you.
Okay.
Yeah,
Okay,
it's just that it will be available to everyone if you want. Yeah,
okay, I'll call you during office hours then.
yeah. Just I think it's the same room. You can just log in.
Oh, okay.
Right, it's exactly the same room. That might be the best. Yeah. How's your research going on?
It looks good. We're thinking of publishing something, but
Good.
it's still there. Work is still left. I wanted to get the results which I got in a better form, basically. But essentially, the idea is there.
Good. That itself is a big step. Yeah. Good. Yeah. Okay, let's I think begin. It's 9:40. I think. So hopefully can join.
Ken is here.
Oh, can see it. Okay, right time.
Back.
Ken, you there yet?
Yeah. I'm sorry. I'm having some issues with my laptop and other stuff.
Okay. I was wondering. Yeah.
Yeah, I had to join by my phone.
Yeah. So you want a few minutes or you're good?
If you could just give me like 2 minutes, that would be
Yeah.
great. Thank you so much.
Yeah. So we can. Wait. So while Ken is joining, Harsha, have you taken a classical mechanics course earlier? Like.
Yeah, I did.
Okay. And this was back in.
I think 2014, yeah, 2014, 2015 probably.
Oh, that way back. How come it is that way back?
I actually did a 5-year integrated MSc course. Since from 2013 to 2018, I think. Yeah.
But then this will be an undergrad course you're talking about, right? I was saying graduate level.
Graduate level. Well, I had 2 courses: CM1, Classical Mechanics 1, Classical Mechanics 2. I don't remember when I did my Classical Mechanics 2, but that would be more or less like a graduate level course.
Okay. Yeah.
I think I did it in my 4th year or something. I think so.
Yeah, then that makes more connection. Yeah. So I thought you took a break for 1 year. So you took a break for longer year then, a longer time then.
No, it's 1 year, I think. I graduated in 2019, right? If I entered in 2013, is that right, or is that wrong? Wait, I joined in 13, right? And 18 I graduated?
Okay, yeah, it doesn't matter.
Yeah. And then what? Yeah, I spent 18 to 19, 1 year, break. And then I joined, fall 2019 I joined, I remember. Yeah, that makes sense.
Good. Ken, how is it going?
I think I'm joining on my
Oh,
computer.
yeah.
Okay, cool. Yeah. Thank you so much.
Okay. We still don't see you though. It's up to you. I'm just telling you so that you are aware. Yeah. Oh, I think he's lost.
Yeah.
Okay. So there's a homework too. You on Tuesday. It should be relatively straight forward. Usually we do this in undergraduate physics, at least in some of the courses. The drag forces that you come across, not a very fundamental equation, though if you look at it from the Stokes flow point of view, if the linear drag actually can be thought of as a fundamental equation, because in the extreme limit of small Reynolds number, that does come out that way. But otherwise, the homework itself you should find it easier than the first one. And we have midterm 1 coming up, so it's March. I shouldn't say coming up, but it's relatively far. So that's is that readable, Harsha?
Yeah.
Yeah, right. I can zoom in also, but sometimes I hear both ways. There is a bird's eye view, and so let me know, okay? If you want me to zoom in, fine. Ken, are you good? Oh, you lost him.
You're muted, Ken.
Oh, maybe he's muted, you think? Yeah.
No. Ken is muted. Like, I think he muted his mic.
There are only 3 of us. We can keep it unmuted all the time, so that's not going to be too much of an issue. But yeah, it's up to you guys. But I think Ken is having trouble with his internet.
Sorry, yeah, I'm trying to like make it so I can hear you guys better, and now it's like connecting to something like Bluetooth. It's just I'm having a very hard time today. I'm really sorry.
Okay, maybe I will begin then. We'll see. Yeah, there's always a recording available, so it should be not that bad to do. Let me give you a few more minutes because I want to start something straightforward, but it's kind of the basic stuff for the whole course. Like we want to start.
Yeah, I mean, I think I think I'm at a good spot now, so I'm sorry about that.
So Harsha, you did get a chance to go over the course webpage. Was it accessible, the recording? You're aware of?
Sorry, I couldn't hear.
Yeah. Maybe Zoom sometimes makes it. Yeah.
Hello?
I was telling you, Harsha, that you know that the recordings for the course lectures are available on the
Yeah,
webpage.
I do know. I watched the first one. I have to watch the other one that I missed.
Yeah, no, it's up to you, but I just wanted to let you know that
Yeah.
they're available. If you reach the course webpage, that should be good. Yeah.
Mhm.
Okay. Um, so we saw Newton's law. Right? So Newton's law, just to write it down, but that's not what we're going to talk today. So let's write it as d by dt, mass times velocity is equal to forces, right? Sum of all the forces. And let's write it as, in particular, it turns out that it is a function of r, position, velocity, and time. One could ask, can it be a function of acceleration also? Good question. I think the answer then would be that if there is an acceleration, why not put it on the left-hand side and work it out like that? But I do know that there are forces that are dependent on acceleration, like radiation reaction is an example. Yeah, how about this? So I leave this open-ended questions where I don't have an answer as a quiz. So look up or think about can forces be a function of acceleration? How does it go? Usually we always say in the way, a fundamental way we are trying to put it, it's only the position and velocity. Can force be a function of acceleration? And in fact, then higher derivatives are also like what's the implication of that? Like, is there a redundancy in that, or is it sufficient to say that it's a function of position and velocity itself? So without answering that question, basically I don't have a very clear, solid answer there. But what was observed is that, remember that in 1660s, also Newton's law came up, and it was extremely successful in the sense that you could explain planetary motion using this. And of course, you could also talk about dropping a stone on the surface of Earth. And very soon, during the time of Laplace and Lagrange, it was realized that it can also be written in terms of energy, and in more general, there is a function. So you could think of a quantity. For now, let me just say it's a quantity. We will call it the action. Right? So you could construct a function L, which is dependent on position, velocity, and time. And also remember that this is the position of the object that is moving. So this is having an implicit dependence in time. Like velocity has an implicit dependence in time. And actually, in this Lagrangian, we can actually explicitly write that. Right? So this t velocity as a function of time. and it's implicit, and that will play an important role as to what is an implicit dependent and what's an explicit dependence. In fact, we will call it a dynamical variable versus a normal variable. We'll differentiate those quantities. It will come out reasonably naturally. And you define a quantity as an integral of this, evaluated from some time t1 to t2. Okay. It was realized that if you try to minimize, like it seems like the nature is having a feel for this quantity, and it tries to minimize this, and this is called the Lagrangian. We will see later, but I'm just motivating at this point that it was realized very soon after Newton gave his equations within 50 years or within 100 years or so, that it is probably more useful to think of Newton's law as coming out of this, and the system is trying to, so system tries to minimize or maximize the above quantity, right? I'm going to define it as a functional later on and so on. So I'm not saying it's a function because what we are saying is that for all possible parts of the system, a minimization principle will pick that particular path that the system takes. So, so notice the word minimization. In general, we know that nature tries to minimize energy and maximize entropy. So those are the two interesting or two basic phenomena that we see. And so now we need to learn how this minimization principle works. So before I come back to this, so this will be called the stationary action principle. Stationary action principle. And we'll have to come back to that instead of or Hamilton's principle. Not everywhere you call it the Hamilton principle, but in general, I'll call as a universally stationary action principle is the name given to this observation. Instead of looking at this, let us do some similar systems elsewhere. And again, historically speaking, it was known that there are other systems where a minimization principle explains something that is observed in nature. And we'll try to understand that and do some other similar problems. We'll spend some 2 weeks or so. This is a new mathematical technique we'll have to build for this. So we'll spend probably 2 or 3 weeks on that, and then come back to this and actually do the actual physical problem, which is the Lagrangian mechanics, and work on actual problems. Probably 2 weeks at least, let's say. Okay, so let's do a simple system. Where else do we see this? And you might remember Snell's law in optics. Completely different, and that's what we are going to do in the next couple of weeks. We'll do a lot of examples where minimization sort of explains the basic law governing the system, and it will be from all over the place. It may not be specifically to mechanics alone, but we'll come back to mechanics and use those principles. So what is Snell's law? Let's remind ourselves. Snell's law is, let's see, so you have a two regions of space with different refractive index, correct? So this is, and 1 is a refractive index on left side, and 2 is a refractive index on the right side. What is the refractive index? Refractive index is an I is always larger than 1, right? So it is the So speed of light happens to have a maximum value, which is the speed of light in vacuum, and you divide it by the speed of light in the medium. So it's the speed of light in the medium. So that's refractive index. It's always greater than 1, or greater than or equal to 1. So if you have two regions, one could be glass, one could be air. Air is pretty much like vacuum itself, so it is very close. But for our purposes, we just need two regions. And we are the law says that if there is a ray of light, or this light itself is understood in terms of electric and magnetic field. But long before Maxwell gave his equations in about 1860s or so, before that it was thought optics is a completely independent field in a sense, and it was understood in terms of ray optics, basically geometry of straight lines, like geometry of straight lines and interacting with interfaces, which could be curved, explained most of what we see in geometrical optics or ray optics. And when is that true? When the wavelength of light is significantly smaller than the the roughness of the interfaces. If it is significantly smaller than the wavelength of light, then it is a good approximation to use ray optics. Basically, you're neglecting diffraction in that scenario. Okay, so if there is a ray of light coming in, and if you have an angle that you can measure with respect to the normal, so that's θ1, and that's your normal perpendicular to the interface, and a ray of light, if instead of going straight, it can either bend away from the normal or closer to the normal. So if N2 was greater than N1, then it will bend towards the normal, and we have all seen this, right? So, and Snell's law tells that N1 sine θ1 is equal to N2 sine θ2. And often, we see this quite early in our schooling. If we studied science, it comes very early, like even before high school, probably. So, can this be explained in a different way? And yes, there is a minimization principle here, and the idea is that when light is going from one point to the other, it tries to take the path which has minimal time. So it tries to take the shortest, how do you say? Yeah, not shortest path. It takes a path which has the shortest time duration that it takes to reach that, and that's called the Fermat's principle. And this was again known way early. It's almost like saying if you were walking from one region to another region, and there is concrete on one side. So, for example, let's say this is concrete and this is sand. Right? If you think of a physical problem where you want to reach from one point to the other point, so that's your concrete, and this could be sand. That's concrete. And usually, typical humans can walk faster on concrete. And if you are to walk from one corner of this region to the other corner, then you would like to spend more time on concrete, right? Because you can go faster, and less time on sand. And the same principle. And then you can ask, why not go all the way in concrete and go on the edge and go perpendicular in sand, least amount of time. But then the path, the distance you're traveling is too much. But if you go diagonally, then you're not giving a preference to the concrete. So there's a give and take there, and there is somewhere there is a sweet point where the time is really minimal. And the idea is to find that minimal point, and it satisfies the same equation because it's again the speed that is coming up, right? how fast you can travel in concrete and sand. And it will be exactly here. You won't talk about a refractive index there. Here you'll talk in terms of velocity. So let's derive this minimum principle here. And what we are going to do is do this for 2 regions, then do it for 3 regions, and slowly increase it and get a function itself out of it. And we want to see the specific assumptions we are making in this derivation so that we can do this as a generic statement of what will be called the calculus of variations, or we will use the technique of what is called functional derivative in here. So, so mathematics will pretty much follow whatever we are going to do for this example. And this example, we'll try to make it as clean and simple as possible. Okay, so going back to this, let me draw this figure again. So let's say, let me have a box-like structure. So that's your interface. And let me say this is x1, y1. Notice I'm keeping this fixed, right? It's necessary that at least in the early points, I have to keep this fixed. I can ask the question that what if this itself is free to move around? If light has the option to be anywhere on this line, that's also an independent problem. But for now, we are saying that this is fixed, x1, y1, and x2, y2, that's also fixed. And you have to go from one point to the other. And of course, there's a diagonal line if everything was constant. So that's the diagonal line there. But we know that if the speed is different on the 2 regions, which is characterized by V1 and V2, or which is C over V1 and C over V2. It doesn't have to be like some velocity. Velocities are different. And we can, this is exactly half of this. So we are saying that this is, this point here is x2 minus x1 divided by, no, what is it, x2 plus. Yeah, thank you. So x2 plus x1 divided by 2, comma, it could be, since this is y1, so that's y1. Right? That's that point. And somewhere here, then we have y, right? So this is x1 plus x2 divided by 2, comma, y. Oh, sorry, that's the halfway, but I want to move this around. Sorry. Going ahead of where I should be. So let's say this is actually, there is a particular path down here. And that's that, right? So that point, I say, is x. So this is x comma y, let's say, for the time being. Right? But x is understood to be this. And I would like that point to be variable in that sense that y is the variable there. This is fixed along that line, which y is most suitable for this region. And we know that, so we have to calculate the time, right? So what are we trying to minimize? What we are trying to minimize is total time t, which is the sum of 2 quantities, t1 plus t2. And t1 is the time taken to start from 1 to this y sub arbitrary point y. And let's say this is t1 will be distance traveled. So distance by velocity is time. So let's say this is s1 and that's s2. So s1 over the velocity v1 plus s2 over velocity v2. What is this a function of? This is a function of y alone, right? That's the only free parameter I have left. So that's a function of y. So this is not a This is a simple calculus problem, not really a function here. So simple one parameter problem. Uh, right. So yeah. So that's our problem. And what is S1, right? So we can ask what is S1 and what is S2. Both are functions of y. So let me specify that. So S1 is square root of the distance between them, right? So this is, how do you say this? So this is x minus x1, the whole square, plus y minus y1, the whole square. Remember, x is a function of x2 and x1. So even though I leave that as x, it's not a free parameter. And then just the square root of that. Same thing for S2. It is y2 minus y1, x2. So I can write this as, since it's a square, so that's x minus x to the whole square plus y minus y2 the whole square. Right. Both are functions of y. So if I want to minimize this quantity, so v1 is constant. So remember, what is our philosophy here is calculus says that if you have a function of y, then I had to minimize my dt with respect to y is 0. Simple, right? So it's a, so if you were to plot this t as a function of y, it's just one parameter problem. So there's hope is that there is some maxima or a minima. So this will be actually a minima, right? So there's a minima there, and at that point the slope is 0. Right? That's a simple idea. So dt by dy has to be 0. That means I had to calculate my derivative with y. So S1 has to be calculated. So let's do what is the derivative of t with respect to y, which is just the same as 1 over v1 s1 over dy plus 1 over v2 s2 over dy. That's surely correct. What is ds1 over dy? That's in fact we can do this both in the same go, right? So because they're exactly similar. So ds I over dy, where I means either 1 or 2, then you have take the derivative, correct? So this is 1 by 2 times, when I take the derivative of a square root, it goes in the denominator. So 1 by 2 minus 1, so that makes it go in the denominator. That's xi squared plus y minus yi squared. Right. And then I have to take the derivative with respect to the argument of the square root, and that is 2 times y minus y1. yi. Okay. Will I get the negative sign clearly here? We'll see. And the question comes, can I write the other way or not? Okay, hopefully we'll get that. Okay. So that's your derivative, and the 2, of course, cancels out. But before we proceed, we can actually say one thing. What is this? So if I cancel out my 2's there, as the distance y minus yi divided by the si. So what is y minus yi? So let's look at our picture here. That's y minus yi here, right? It is y minus y1 is this, and y minus y2 is the remaining part on that y-axis. So if I were to define a quantity θ1 here, and same thing here, θ2, which is similar to your Snell's law equation, right? So this will be θ1 and θ2. Then you learn that one is sine theta, and the other one is actually minus sine theta, because it is y minus y2. It should be y2 minus y is the height. So you learn that derivative with respect to t over y is equal to 1 over v1 times y minus y1, that's your actual sine theta 1. And the second one is minus of that because it comes out as y2 minus y. So that's equal to minus sine theta 2 over v2. Multiply by c if you want. Right, then you get c over v1, c over v2, and we immediately almost see the solution. So this is equal to n1 sine theta 1 minus n2 sine theta 2. Correct. That's the general for any particular path. If we define the time t, the change in that time with respect to that point y is given by this expression, and our minimization principle is just a one parameter problem. So it is just the derivative or the slope of that function has to be equal to 0. You set that equal to 0. So notice the point here. So minimization. This is a principle. If I minimization, if I require this to be true, that means the t by dy has to be equal to 0. That implies, right? So if I make this to be my law, that the time taken from one point to the other point is a minimum, then Snell's law comes out as a consequence of that, which is always nice. You have one equation, and if you know that it's coming from a nice little principle, like a more general principle, if you want, like which is more universal in nature, like there are other systems that is trying to minimize something. So that's always nicer. So in that sense, this is a minimization principle. That's okay, that's good. But now we can immediately want to do more than this. Correct? It is just not one interface we want to talk about. We want to talk about a refractive index that's actually a function of position itself, and we can say it has there is there are layers of refractive materials, and the refractive index is continuously changing. So let's think of a simple system where you see that, just to motivate the problem, and so that we can actually. Was it readable, Harsha and Ken?
Yeah, I could
Okay.
follow.
Yeah, no problem.
Ken, have you settled down? Yeah, it seems
Oh
like.
yeah, I got everything under control. Sorry about that.
Okay, so this is good. This is just this is a classic example where we have glass and air. But now let's think of a more elaborate problem, right? So this is just to motivate. So if there was ground here, so this is ground, and let us say sometimes on a very hot day, so this could be concrete. Let's say this is concrete, or in a desert, this is very common. This is the idea of what is called as mirage. On a hot day in a desert or on an interstate, the surface of the ground is extremely hot, and the temperature gradient is upward. Temperature goes temperature. It's very hot on the ground, and it gets cooler away from the ground. And you might have noticed that sometimes if you stand, and if you could be driving typically on an interstate, that's where it is most common. But if you have been to a desert, that also you see this. So there is a person standing, and if there is a tree, so this could be a tree. So that's a tree or some object that's way back. And if you want to see that object, of course, one way is that you actually light goes all the way in here, right? So that's how you observe. The light comes from one point and reaches the other point. But our eye has this feature that it can only sense the angle, right? The way ray optics works is that you look for two rays of light, and when our eye, so this is again just a model. So that's your eye, and let's say there is two rays of light coming in. So let's say, so that's your two rays of light, and we are used to, our brain is smart enough to realize that if you have two rays of light coming in, it will project itself backward and it can sense this angle theta. And based on this angle theta, it can actually tell you where that image is found. So this is the distance d. So you know that, oh, there's a source of light there. So that's a processing that our brain is doing. Obviously, our brain doesn't know whether this object is really there or not. And the classic example is a mirror, right? So if you have a mirror and you have rays of light coming in like this, and if I draw backward, right, so that could be the source of light. So light is here, but let's say our eye cannot see this object, so there is a screen here. So it doesn't know that this is the source. And again, our eye will see this, but our eye doesn't know that there is a reflecting material there. What it will do is that it will project it backward. So this is your image. And if not for experience that, okay, you see this and this together, when you first time see it, you will assume that that's actually the object. For if it was a perfect scenario, our brain cannot tell the difference between an image and a source. So with that simple analogy, we again do the same thing here. So there is a ray of light that horizontally goes in, since and remember that refractive index depends on temperature. Refractive index depends on temperature. So in that sense, there is a layers of refractive materials there, which is continuously changing in time. And because of this refractive index change at each layer, there is another light, like which obeys Snell's law. It comes here and then bends it. It happens continuously, but it's a good way to look at it as layers of refractive index. It goes away from here, so like this, and the idea is that this actually bends backward, and this involves the idea of total internal reflection, right, which all of us are aware. Like Snell's law has this feature that beyond a certain angle, if you're going from a dense medium to a rarer medium, there is no more refraction, there is only reflection happening. That's good. So this is what happens. But as far as our brain goes, it doesn't understand this whole process. It will actually go backward, right? So this will just project the ray that is reaching the eye, project backward, and it sees an image of this point, right? So it says the image of an object. Usually, if there is a tree or something, you see the image of that, or anything that is in there. And our brain also has the experience that whenever you see the image under the water, it seems like there must be water there, and so it looks like water. That's a very broad description of the example that we want to do. The main idea is that there is a refractive index, which is a function of position, and we would like to analyze such a problem. So the idea is, if you have, in this case, n is a function of y, right, where y is going upward. Refractive index is a function of y, not just two mediums, to an interface having a boundary. Then, if you have 2 points in there, here, this one and this one, what is the path that the light will take? And based on Fermat's principle, we can argue that this will be coming out from a minimization principle. So we want to attend to such a problem. So let's build towards that. and go slow and keep track of what are the assumptions we are actually making. So in that approach, let me do the same problem of we have 2 medians, but this time we have 3. And this horizontal lines are not really important. We can extend it there, but we are keeping this fixed. Right? So this time we will make it 3 regions. So let's say this is again fixed. We want to talk about the light starting from this point. We're not giving it a choice that it can start from any other point. It also has a constraint we are putting in the system if you want. And later on, we want to understand more of that also. Again, this is the free part. So we will say this is x comma y. Somewhere here is x comma y, not at the center. So this is x comma y, and this will be x comma y1 at this point here. And somewhere else, I don't even want to say that it is on that side. So somewhere here is x comma x prime comma y prime. And let me say this is okay. Notice I purposefully put the x prime y prime down there, but it depends on actually what the regions are, n1, n2, and n3. So in principle, everything is allowed. But if it was a proper gradient, then expectation is that eventually this will become a curved quantity. Right? So this is n1, n2, and n3 is given, which means that the 3 velocities of those 3 regions are given to us. Again, let's have the angles with respect to this to be theta 1, and let's say this is theta 2. That's theta 2, and here this should be that's being yes, measuring the angles with respect to the horizontal in the upward direction. So this will be sorry, this is theta 3. So this will be theta 2, and this is theta 2, so that will be negative in principle. So again, the same idea. So this is x prime comma y1. Same idea. T is equal to t1 plus t2 plus t3, and in general, we have t dependent on 2 parameters this time, y comma y prime. We have 2 parameters, that's the difference, and very soon we want to make this continuous. Okay. So that's equal to P1 is, let's say this is S1, that's S2, and S3. So that's S1 over V1 plus S2 over V2 plus S3 over V3. Right, that's your 3. Like we had earlier, let's multiply by C1 right away, C right away. That's your C, C, and C, and that is a C times a T. That way we know that this is N1 times, so that's equal to N1 times S1 plus N2 times S2 plus N3 times S3. We want to minimize this. Now notice the point here, when we want to minimize this, now there are 2 parameters, and we are asked how do we go about this minimization problem, and we are going to say that y and y prime are completely independent. So there is, you're going to say y change in y does not make any requirement on the change in y prime. So the variation in y and y prime is going to be completely independent. So let's see where it shows up. So let's say what is the derivative here, right? So c times so let's say dt with respect to y, that's equal to same idea. So what does S1 and S2 depend on? Correct. So let's let's write this explicitly. S1 is equal to, so that's x minus x1, right? So it's x minus x1 squared plus y minus y1 squared. This is simple because this depends only on y, right? So let me state that. It's good to bring out that feature. So this is y comma y prime. This is n1 times s1 depends only on y. What about n2 or s2? What does that depend on? That depends on both y and y prime. That's correct. So that's y minus y prime. So this depends on y and y prime. And the third, S3, as you can see, this will depend only on y prime. Okay. So let's see what we do next. Next, we require that this is equal to 0, and our requirement is going to be both the derivatives has to be 0. So that's a requirement now. When we say the minimization principle, we are saying that dt by dy is equal to 0, and we will require that dt by dy prime is equal to 0. And we are also going to say, this is inbuilt in this, that y and y prime are completely independent. In this case, it comes out very natural that like first I keep this fixed and change as completely independent of y prime. So that's an additional equation I have to write. If I were to write it as a partial derivative, I will say this is y with respect to y prime is equal to 0. Okay. Later on, we are going to see this in a different setup altogether. That is why, in principle, if this was if I had a lot of y prime, and so on. So y is a function of x, correct? So later on we will talk about change in. So this is a futuristic thing. So there will be a lot of y's as I increase my number of points, and a change in y with respect to change in y at another point x prime, because very soon I will stop tracking it as y prime, y double prime, y triple prime. Instead, I will say that each of this y is a function of x. So I would require the variation at each point in x to be independent of the next point. Right? That's a requirement that is coming from the minimization. And then I have to ask, okay, that's 0, right? But now if x and x prime are continuous, this is equal to 0 if x is not equal to x prime, which raises the question, what if x is equal to x prime, which is a variation in itself, and I would like it to be 1, right? If it is, or let me not say it is 1, let me say this is, what is this if x is equal to x prime? So that's a question, I'll leave it open, we'll come back and answer that. And so if it is discrete points, then that should be 1, that's correct. But if this is not discrete points, if this is a continuous variable, then I will argue that actually that's not 1, that has to be infinity. Like because it will have the property of a delta function. When you add up all these change in variation, like the idea of an integral, integral is basically adding up a lot of quantities, that's correct. But integral is adding a lot of infinite set of points, each of which is infinitely small. So adding infinite quantities, but each one is small, can lead to some finite quantity. And we want to bring that or motivate that in here. So I'll leave that open. But for now, this is the important point. Right? This is independent of each other. In this case, sort of a trivial statement, but I want to stress on that fact, because later on that will become a big conceptual issue as to what do we mean by that. Is that okay or not? So keeping that or emphasizing on that, let's keep going. So what is dt by dy? And that's we have already done, right? So now when we do dt by dy, it's clear that, oh, this doesn't, this depends on y, this depends on y, third one doesn't even depend on y, and we have done this as with respect to y, right, earlier. So this is nothing but n1 sine theta, right? When we take the derivative, this comes out to be n1 sine theta 1. And taking the derivative with s2, let me, maybe it is a good idea to just do it, right? So explicitly, so this is s3 is also equal to x2 minus xx prime squared plus y3 by 2, y2 minus y prime squared. And just to clarify, this is ds1 over the dy is equal to y minus y1 over s1, which is sine theta 1. Correct? What about ds1 with respect to dy prime? That's equal to 0. And it does not depend on y prime at all. What about s2? Derivative of s2 with respect to y is y prime minus, notice y prime doesn't depend on y, so it's independent. That's y prime minus y divided by s2 here. And y prime minus y, assuming that theta 2 is positive, so y prime help. Did I write y prime minus y or? Yeah, that's correct, right? So that's yeah, so that's sine theta 2, right? How did I get the negative sign there? I was confused there. Oh, because it was a distance, right? Yeah. Yeah, help. Yeah, help me.
The dou s2 by dou y, that y and y prime I think are interchanged.
This one, is it?
Yeah.
Because it is y minus y prime, right?
Yeah, if you would have used y prime minus y, then you would get a negative sign again to correct it.
Yeah. So relatively that is 1, right? So actually, yeah, I wrote this like, let me be consistent, right? So I mean, it doesn't matter what I do. It should correct it on its own, right?
Mm-hmm.
So here, if I were to write y prime minus y, so this is, what is this? Oh,
You
now
get
that is
negative of because there's a negative y in that.
this is negative of y prime minus
y.
Right? And that is minus sine theta 2, correct? And this one probably will come out the opposite. Let's see. So ds2 with respect to y prime is equal to, y prime will be the positive version of that. So that's y prime minus y divided by s2, which is sine theta 2. Agree? I think that's correct. Okay. ds3 over dy, that's equal to 0, and the partial derivative of the third distance with respect to y prime is, now again we see this minus of y2 minus y prime over s3. A little worried about, it seems like it depends on the way I write it, but it is a relative quantity that matters, I suppose. Right, that's equal to This is minus sine theta 3. Good. Right. So notice like the structure we are forming is that if you think of this as a 3 by 3 matrix, because once we extend this further, this will be sine theta 1, 0, then that is, it's not a 3 by 3, right? 2 by 2. Why am I getting 2 by 2? Because there are two variables in between. So in principle, that's 2 parameter derivative. So this is minus sine theta 2, and that is sine theta, again, that's sine theta 2. And this is 0, and that's minus sine theta 3. That's your structure. Corner ones get a 0 on one end, and otherwise this keeps stretching itself. So partial derivative of t with respect to y. First one gets this, and the second one is ds2 over dy. So that's minus n2 sine theta 2. Right. And the third one does not contribute, so that's 0. And we have partial derivative with respect to y prime. That's equal to 0 coming from here, and y prime is n2 plus n2 sine theta 2 minus n3 sine theta 3. And we have to set this equal to 0 each time. So this is equal to 0, that's equal to 0. And our Snell's law now says that this is n1 times sine theta 1 is equal to n2 times sine theta 2. And we have n2 sine theta 2 is equal to n3 sine theta 3. It's sort of the way we did it, it is easily generalizable. What if this was 3 regions becomes 4 regions, and 4 regions becomes n regions? It is clear that at each interface this Snell's law is obeyed. That's perfectly fine. So what we would say is that if we had x, right? So if there was an x here, and the next one is x plus, like we are making this really close by, so that's x plus dx, let's say. Right, that's your next point in here. Then you would say that n now, which is a function of x, and sine theta, which is a function of x, has to be equal to n at x plus dx and sine theta at x plus dx. So this is a function of and again, you will see the derivative concept coming in here, right? So we seems to suggest that this is the derivative with respect to x, right? Derivative with respect to x of n x times sine theta x that is showing up. But for that, we need to derive the divide by dx and take that limit, right? So it seems like there is a quantity like this that is being, but we want to ask, is this what it means? So is that really what that means? And for that purpose, we'll go all the way back and actually start all the way back with respect to a variable. So we will say, instead of t that we talked about being t1 plus t2 plus t3, right? So there's a large number, you broke it into, like, let's say n, where n tends to infinity, you're actually breaking that into infinite pieces. Then how you would do it is, instead of talking about this, we will talk about an integral. So we would say this is an integral going from the first point to the other point. The first point was x1, right? X1 to x2. And at each interval, that is dt. But what is dt at a very tiny region there? So that's your, this is your dx. And we are talking about from going from one point to the other point, where these 2 points are independent of each other. We shouldn't forget that. So dt is nothing but ds, or n times dt, right? I meant to write dt is equal to n times ds. At each point, it is it's of course a function of x, n of x, times the small tiny ds element, right? So that's equal to x1 to x2, and this is n of x, and now this is ds, right? An arbitrary point ds, and we would like to now change this s with respect to x. So how do you do that? So again, go back to our distance formula, right? That is what we were doing there. Now, infinitesimally small quantity, we know that this is dx squared plus dy squared. So the s would be, if I want to write it in terms of dx, this is ds times square root of 1 plus dy by dx squared. So this is equal to x1 to x2 refractive index, and then we have dx, or 1 plus derivative of y with respect to x the whole square, and dx. And we would like to minimize that quantity, but we'll come back and do this more carefully. I think there is 5 minutes remaining, so I want to do this slowly. What we will do now is, so I sort of motivated you why we should consider instead of a discrete quantities, we want to do this for a continuous variable, and we want to minimize a quantity like this. So what we have motivated here, what I've motivated is, I would like to minimize t, which is an integral going from x1 to x2 dx, if you want, times the refractive index, which is x, and 1 plus dy by dx, the whole square. But notice here, n is fixed. That's what n is a given function. So this is a given function. There's no choice there. That's a given function. What are we solving for? Y, right? Y is a function of x. In what sense is that? Earlier we said there were 3 points. There was a y here, there was a y here, and there was a y prime here, right? So that was y prime, and but in general, if I were to keep breaking this into smaller pieces, this could be an arbitrary function. And I'm looking for that function, and that's that function y that is sitting here. And I'm looking for all such possible values. That's what we're looking for. So what is it that we're interested in? T is a function of a function itself. Right? So this is y, which is a function of x, but we will stop showing that, and we will change our parameter to a square bracket to represent that this is a function. So this will be called a functional. it means that so this should be read out as this is y of x, right? But for all possible functions, I don't know what that function is. Like if I know the function y, then this is a function of y. But this is all possible functions. Right? Think of every possible function like tangent x, exponential x, any function, and one of them is going to be picked out by the minimization principle. So that's going to be our goal. We'll make this more formal. I'll come back and do this. I don't want to jump into it right away. Hopefully, I've motivated it to a certain extent, and I'll do that. This will be called a functional derivative, if you want. Okay, any comments or questions?
I have one question.
Yes.
Like for example, in the mirage example that you gave us, if there are two paths which which light can take, then given the beginning and the end points, then when you minimize it, only one of them should be the least. Right?
No, if there are two possibilities, then both are solution, I suppose, right? For example, let's say, I'm just thinking, if there are two solutions possible, then both are allowed in principle. I don't think it will be one, but in general, it will always be one.
There should be like local minima then, right?
Oh, yes, local, I mean local minima in all this. Yes, that's correct. Local minima here means that there is one function. But I think, is this what you're trying to tell? I mean, I'm not sure what's your motivation. So are you trying to suggest that this is also a solution going straight?
Yes.
Right.
And one is definitely shorter than the other because one is direct.
I think here the point is, that we also, I'm wondering if there is a question about setting the derivative here, right? So, because there's also another path like this, right? Light can also go this way. I think the point is that light has to come from here. If you set the initial direction, then there is only one path, I think, because otherwise there are many paths possible. Like there's a bunch of, that's why you get these rays of light that is coming in. You'll get a cone of light. But we will be doing this very specifically, we will be doing it very specifically in the sense, I will give you an n which is most like basically square root. If n is square root of y, that's a good representation of this problem. And if I recall correctly, we do set the derivative also there. I think so, right? But that's a good question. Yeah, I will say, let me leave that alone at this point. It's again, if you add a sheet of paper, right? You can ask, what's the shortest path from going to here to here? It's of course a straight line. But now I'm just saying, yeah, keep that open. I think the derivative catches that. That's my guess, but I don't want to, I'm not seeing through it completely. I think
when we solve that problem, I think it'll get it'll get clear.
Part of it will be homework. I think I do one of the problems now that you brought it up. So probably I'll do the square root function, this mirage problem in the class, and to do another problem in the homework. Yeah, so there's a whole class of problems on this. Yeah, good question. Yeah, I think it is somewhere you set the derivatives also. Yeah, down the line. Good. Yeah, so that'll leave you also with some open questions. Okay. Okay, but good point. Ken, how was it?
It was good. Yeah, no problem. No questions.
Is this okay to keep it in this Zoom level?
Yeah.
Okay then, good. Yeah, good question, Harsha. Shall I stop?
Yeah, I'll see you.
Yeah, you have concerns. Yeah, ask me.
No, I just said see you.
Oh, see you. I said, let's see. I heard. So I thought you're still bothered about something. Yeah. Okay. Good. Okay.
Okay.
Okay. Bye bye.
Bye.
All right, goodbye.
Bye, Ken.